Ora, vamos então ver a próxima apresentação. Esta será uma exceção, será uma apresentação em inglês pela Douaa Elbashir. Portanto, a Douaa é engenheira civil com mestrado em análise estrutural de monumentos e construções históricas pela Universidade do Minho. Tem 6 anos de experiência profissional em projeto estrutural no Sudão e atualmente encontra-se a trabalhar como investigadora no Instituto Politécnico de Leiria. E então a Douaa que iniciasse a sua apresentação.
Good morning, everyone. My name is Douaa. I will be presenting today the design and the evaluation of the behavior of the connections in the pre-shell project. My presentations consist of 7 main aspects: a brief introduction about shells, the project outline, the distillation method, the connection system, the experimental campaign, and accordingly numerical simulations and some conclusions about the work. To start with a brief introduction about concrete shells, as we all know that the shell industry has been stagnant for quite some time for many reasons. To state only a few, the expensive and the unique molds required to construct shells, which is a very important aspect and one of the main objectives that we later address in the project. The limited workmanship, the experience and cost of labor, the tedious construction methods, and the impractical morphology in most cases, adding to that the complex structure analysis and the limitation of the building codes. However, recently the shell industry have witnessed a rebirth because many of these reasons now some solutions have been developed for many of the obstacles. To state a few, there are constantly some new production and construction techniques developed. There are many advances in computational capacities. We have now better understanding of the construction materials, and we have better and wider access to testing techniques. Adding to that, the environmentally aware design ideas of today. A quick outline for the project. We have the shape finding process to start with, the material characterization, the distillation methods, the connection development, the reinforcing system, the structural design, construction planning, and of course leading to the end of the prototype production. In EPL, our tasks were focused around the distillation method, the connection development, and the construction planning. To start with the shell distillation and the connection development, the distillation of the shell was a very important aspect leading to the development of the connection, given that it's very important to know how the shell is going to be divided into how many sub-elements to decide on which development, on which system of the connections we are going to use. The distillation is very important on deciding how to minimize the number of the different molds used and to develop reusable molds, which is, as stated before, one of the most important aspects of the project, to reduce the cost and to reduce the production time, and to facilitate also the transport and the de-assembly in the future if desired, and of course to provide structural integrity and stabilization to the project. As we can see here, and as stated before, that the shell is divided by its symmetry planes into 3 main sub-elements. Now, to develop the connections, we have divided these 3 sub-elements each into 4 small sub-elements, which translate later to 4 molds that are going to be used for the production. This gives a total of 12 sub-elements forming the entire shell of the structure. As we can see here, a photo of the 4 sub-elements and how the connections are developed within these sub-elements. We have an indentation, a male connection, and a female connection. This is a small preview to show how the connection system is developed and how the sub-elements are linked together. It's as I stated, it's a staggered tooth male-female connection using an interlocking joining method to make sure that the elements undergo pure compression. It's a dry connection, and the dry fit is set to facilitate the assembly process on a dry construction, as well as the deassembling process if desired in the future, as well as facilitating the fitting between the elements, and to ensure adequate transmission of forces with the added advantage of having a smooth and aesthetic finish. Now to the connection configuration, as you can see here, it's a male-female connection. There are a minimum of 2 connections in each of the internal faces of every sub-elements, and the number of location and the location of the connections was developed in order for it to be completely compatible with the pre-stressing layout that is going to be added. The project, the shell is going to be reinforced with internal monostrand pre-stress. Therefore, it was very important while developing the connections to keep this in mind and to make sure that the connections doesn't interfere with the pre-stress layout. This can be seen here in these illustrations that there is the spacing between the connection was developed keeping in mind the pre-stress layout. In the project, 2 prototypes have been developed, the main prototype and a reduced scale model was set originally for the purpose of testing on a seismic shaking table, in addition to direct quasi-static tests. Therefore, the connections were developed for both of these prototypes, the reduced one and the full one, with the same geometry and the same concept, with different dimensions. Now, to test the connections, we have developed a simplified small model to test the connections individually. And this is the model. It's a simple 60 by 40, as we can see here, with a 7mm thickness, which is the thickness of the reduced model prototype. An experimental campaign was planned to evaluate the load carrying capacity of these connections and to evaluate their capacity to transfer the shear force and to better understand their behavior within the shell. As we can see here, this is a small illustration for the dimension and the location of the connections. In this test specimen, the depth of the indentation was about 3 centimeters. To start with the experimental campaign, we have planned 2 types of tests, an in-plane shear test and out-of-plane shear test. To start with the in-plane shear test, as we can see here to our right, there is a model of the test prototype, the planned test prototype. The 3 concrete specimens were fixed. The 2 side specimens were fixed to the frame using steel elements to prevent any undesired movement during the test. Meanwhile, a force was applied to the middle element through a hydraulic actuator. In addition to an external pre-stressing, the internal pre-stressing in the shell was modeled in the test in a form of external pre-stress using threaded bars to make sure that the connection face is constantly under compression. Here is a close-up of the setup model, as well as to the right, the model in real life. This is what it looked like. Now, to explain a little bit more about the tests, the test was a displacement control test. We used 4 LVDTs, 2 LVDTs in the middle piece and 1 in each of the side specimen. The, the pre-stress was applied using, as mentioned before, a 3 millimeter threaded bars, 4 bars, 2 on each side, and the pre-stress was applied using a cell. Now to the results of the in-plane test. We had 6 tests in total, 2 tests without the pre-stress effect, 2 tests with the first level of pre-stress effect, which is 1 megapascal applied to the connection face, the contact face, and the other level is 2 megapascal. As we can see here to the right, this is the typical failure of the connection. The connection has failed by crushing. The indentation has crushed the male connection, has crushed into the other piece with an average of maximum load of 113 kilonewton with a coefficient variation of only 0.20. We can see here the graph of the 2 tests with the average. Moving to the second pre-stress level, which is 1 megapascal applied to the connection face, we can see here more or less the similar behavior with an additional effect of friction, a small effect of friction around the connections resulting from the added level of pre-stress with a maximum load carrying capacity of 134, which is roughly 25% additional load carrying capacity than the test without pre-stress. The third level, which is 2 megapascal of pre-stress applied, have resulted in an increased load carrying capacity of 190 kilonewton, which is around 40% increase from as compared to the test without pre-stress. As we can see here, the failure was more severe with the friction between the element is more evident and it's concentrated at the top of the connection. Now, to summarize the 6 tests, to our left we can see the graph of the 6 tests. The green color is the test without pre-stress, the brown with the first level of pre-stress, and finally the blue are the 2 megapascal pre-stress. We can see here the typical failure of the pieces, and we can see the position of the failure with respect to the pre-stressing part. Now, some numerical analysis were carried out mainly for the purpose of validation and comparison of their experimental results to understand how the connection is behaving and expected to behave under the applied loads. We can see here at the bottom is an illustration of the node stresses. As we can see, the test, the numerical model was able to predict very well the behavior of the connection. Here we have the normal stresses to the left and the shear stresses to the right. If you can see, if you can look at the connection, at the area of the connection, the behavior is quite similar to the experimental test. Now to the other test, the out-of-plane shear tests. The process is similar to the in-plane shear test. To the right, you can see a model of the test setup. It's the same. The pieces are fixed to the frame to prevent any unwanted movement during the test, and the force was applied to the metal element through a hydraulic actuator, and the external pre-stress as it was in plane test was there to make sure that the contact face is under pure compression. Here is a closer detail of the test setup. As we can see here, jacks posts were added to the outer elements to reassure that there is no rotation during the test. And of course, also with displacement control with 4 LVDTs, 2 in the middle piece and 1 in each of the side elements. The threaded bars used here to apply the pre-stress was also 12mm threaded bars with grade 8.8 steel, and the pre-stress load was applied using a load cell, 4 load cells in each of the threaded bars. On to the results of the out-of-plane shear. Similar to the in-plane shear, we had 6 tests, 2 without pre-stress, 2 with the first level of pre-stress, which is 1 megapascal, and 2 with the second level of pre-stress, which are 2 megapascal. As for the test without pre-stress, the maximum load carrying capacity, the average of the maximum load carrying capacity achieved was 32 kilonewton with 0.14 coefficient of variation. We can see here the failure of the connection. The second level of pre-stress resulted in a failure is quite more exaggerated than the first, with crushing in the male connection and with higher load carrying capacity. The load carrying capacity was 84 kilonewton in this test. Now to the third and final test with 2 megapascal, the capacity has increased over 70% from as compared to the test without pre-stress, with a failure quite slightly different from the failure than before. The failure here in this specimen specifically was a brittle failure with the connection almost entirely intact, and this is believed to be a failure rather in the material, because as it was noticed for this specimen and for other few specimens, that the distribution of the fiber reinforcement around the connection was rather unhomogeneous, and in all the specimens that had more or less homogeneous distribution of fiber reinforcement, the behavior of the connection was more ductile. Meanwhile, when the connection had less percentage of fiber reinforcement, the behavior of the connection tended to be more brittle. Now, just to summarize the tests, to our left we can see the graphs, the load, the force displacement graph for the 6 tests. The green are without pre-stress, and the blue are with 2 megapascal level of pre-stress. To the right, there is a graph, a simplified graph of the average. At the bottom, we see the failure of, to the left, the failure, the brittle failure in some of the specimen where the content of the fiber was not distributed homogeneously. In the middle, we see the typical failure for the specimen with 1 megapascal, and here a general behavior of the specimen under applied load. On to the numerical simulations for the out-of-plane tests. Again, as we can see here to our right at the top, this is the total deformation of the test, and as we can draw a comparison, it's quite similar to the behavior of the connection in the experimental campaign. At the bottom, we have our principal stresses, and to the left, we can see the behavior of one of the side elements of our specimen, and if we can draw a comparison, the behavior is also very similar to how the conduction behaved the applied load in experimental campaign. In addition, numerical simulations were carried out for the full shell without pre-stress to judge on how the connection would behave within the shell. At the top, we can see the foot deformation, and as expected, the deformation, the maximum deformation is at top connections. And at the bottom here, we have the stresses, the maximum principal stresses, and the stresses concentration was more at the top connections. Now, to draw conclusions, in general, the male-female indentation, they failed simultaneously under loading, which signifies a balanced geometry in general. Higher stiffness and load carrying capacity were found in the specimen that were subject to in-plane loading, and fiber reinforcement prevented brittle failures when homogeneously distributed. We saw this in the third test of the out-of-plane shear. It was more evident, and the applied pre-stress increased the load carrying capacity by an average of 40% for the in-plane loading and around 70% for the out-of-plane loading, considering, of course, the maximum applied stress as opposed to non-reinforced connections. And the friction resistance was more evident with the pre-stress application, and specifically with a higher level of pre-stress. These are the references, and thank you very much.